Hello everyone, this is a video lecture for Linear Algebra Chapter 4. Again, I'm doing the entirety of Chapter 4 here. There's actually 8 sections. I'm going to try to go fast. So here we go. 4.1 is talking about vectors in Rn. So Rn, just a capital R with a little n in the power there, is the set of n-dimensional vectors V. And so n-dimensional vectors, and we use vector V, a little arrow thingy on top because I can't bold it all the time. So just a quick little example of what I'm talking about here. We got V is an element of Rn. I guess you could use a little line there or not. I don't know. So V could equal, just as an example, 1, 2, 3, 4, something kind of like that. So that would be of 4, actually. I could replace this here with a 4, so R4, technically. And so on and so forth. So we have a whole bunch of just vectors of a certain dimension. I'm going to graph a two-dimensional one so you can kind of see what we're talking about here. So a vector, if it's been a while or you haven't seen them in a long time, a vector is what I like to call a ray, which is basically just a line that starts with an initial point and goes to a terminal point. So, for instance, let's say I have an initial point and I have a terminal point, and there we go. The ray part is that I have an arrow going from one to another. We don't use this word hardly ever. That's not what I wouldn't even use that around other mathematicians, really. I'm just saying that that's what I remember from geometry days. It's kind of like a line, but with an arrow. Often, though, whenever we're talking about vectors, especially in this class, we're almost always going to be starting with the initial point at the origin. And then let's just say that I had 2, 1. So there's my terminal point. And that vector v there would be, again, 2, 1. 2 for x, 1 for y. So not too bad there. Again, I hope that you've seen this at some point, at least pre-calculus or something for just a whole minute, but that's a nice little review. You could do all kind of things with vectors. U plus v, u minus v, all these different properties. I don't know, 2 times u, 3u plus 4v, something like that. There's a lot of different math you can do with it. There's some particular, I guess you could say, properties that would be important for us to remember and know, is that whenever we're doing vector addition and stuff, there is closure under vector addition. Often they just say under addition, they mean vector addition. And so basically, my u plus v is still an element of Rn. Like, if I add 2 vectors, I still get a vector. We have closure under scalar multiplication. And basically here I'm saying c times u is still a vector. You put like a 3u, it's still a vector. Doesn't really change anything there. We have the additive identity. What this means is that you can add 0 to any vector and it stays the same. We have the additive inverse, which if you add u to something that's an inverse of u, you should result in 0. And then we have the scalar multiplicative identity. It's like big words here. And I know my scribbles are not too good. That's why I'm saying it out loud. 1 times u is still itself. So you can multiply any vector times 1 and you'll get the same vector. I'm not going to do any proofs for this section. I just want to give you a quick little example. So let's say we had 2 times 1, 2, 3 plus, I don't know, 4 times 4, 5, 6. Well, I distribute this first and distribute this first. So I get 2, 4, 6, and then plus, I'd have 16, 20, 24. And then I just add like terms. So 2 plus the 16 makes an 18. 4 plus the 20 makes a 24. And 6 plus the 24 makes a 30. Okay, cool. Yay! Next section. So that was more just like a review intro to what's going on here. 4.2 vector spaces. So a vector space, there's a lot of words here. A vector space V is a set, if I could just say that a little bit better there, a set of vectors where the vector addition and scalar multiplication are defined. So I would say vector addition and scalar multiplication are defined. In a way, I'm saying they exist. They can happen. You can take these vectors and add them. You can take these vectors and multiply a scalar by them. I mean, honestly, you're just thinking, well, when is that not possible? And so, in a way here, I'm just saying it's a big list of all your Rn stuff, okay? Now, I wouldn't say that it's just that, but that's an easy one to go with. I'm sure there's other ones. I don't even know if this class goes into a lot of that in particular, but good enough for just saying, as long as you can do these things, we have this vector space. All right, cool. So let me just give you a quick example of something that would work here. I got, I don't know, 0, 0, 0 is one that'll work. 1, 2, and 3, there's a good set of numbers. I got -1, 0, 0. Just any kind of vectors that you can multiply, you can add together, all this kind of stuff. There's an infinite amount of them. They keep going forever. Can you add these two together? Yes. Can you multiply 5 times this guy? Yes. So all good there. Okay. So there's really not much to talk about there, but we're using both this last section and this section to kind of do this one proof together here. And this is an easy proof. It's 4 to 44. The thing is that the quiz right now, and at the time of this making the video, it says 4-4, but what it really means is 4-3 is on the quiz. So I'm not doing the quiz question here. I'm doing its partner. I think I mistyped on the quiz, and I'll try to fix that later at some point. So, okay. Prove that in a given, probably put an A in there is good, in a given vector space V, comma, the additive inverse of the vector is unique. The additive inverse is unique. Unique means one of. I know often in English we say, oh, wow, that was really unique of that, or review or something. Well, we're just trying to say that was unusual or, different. But in reality, unique means like one. There's only one in the whole entire universe, one. So just keep that in mind. Okay. So I'm trying to say that the additive inverse is unique for any kind of given vector space. Remember that it was that u plus a negative u equals the 0? That's that additive inverse, okay? I'm saying there's only the one that exists for any particular vector that would make a 0. As just an example on the side here, let's just say I had my 1, 2, 3, okay? And I had to add something to it to make 0, 0, 0. Well, I mean, you could see u and negative u. Essentially, I'm just going to subtract it, right? -1, -2, -3. When these add up, they make a 0. Done. What I'm trying to prove is that for this vector here, we have only one partner. We have one pairing that would actually make the 0. You could never put a 4 there and still make a 0. It won't work. So I'm proving that there's only this one partner that goes with any particular vector. Okay, and again, it's abstract. What if I had done 4, 5, 6? You see how it's going to not be the -1, -2, -3 anymore. I'm not going to say it's one single vector. It's just it's a partner. It's a pairing of some kind. So I have to keep it all generalized as well. I think the best way to do this is proof by contradiction. And on the quiz, the 43, I do the same thing. I think I even hint at it. Oops. I even hint at it in the quiz. I say, hey, use a proof by contradiction. So proof by contradiction, I would say, just when you're going to do something like this, go ahead and tell me way ahead of time, just so I'm not confused, because, I mean, I can get confused pretty easily. So this is a proof by contradiction. I'm telling you ahead of time. Okay. So suppose that v vector is an element of this v space that they're talking about. And let's make an x vector also part of v. I could have probably compressed that a little bit, but whatever. Such that st that my v plus the x is equal to 0, yet x is not equal to negative v. Okay? I'm saying that we have we have this one vector that I'm going to be able to add into with v to make it 0, right? This other guy here. But I'm saying that it's not equal to negative v. It could be a negative 4 instead of a negative 1 or something like that. I'm saying there's a different one out there. It's not equal to this guy. Okay, this guy I know would add up and make sense. I mean, obviously, v plus a negative v equals 0. That's like, that's given already. I'm saying that x is not this guy, x is some other guy, and it still makes a 0. Okay, see how it would no longer be unique. Okay, so that's my point that I'm trying to make there. Okay, trying to get my scribbles out the way. And so what I'm going to do here is I'm just going to start with my statement that I have. V plus x equals 0. And I've been, on my proof, I use this little implies or like next step kind of thing. And I know I overdid it. You don't have to go so far as I do. And so I subtract x on both sides. This right here we already know yields a 0. You don't need a 0 vector, so this is just this guy. I'm just cleaning it up. And here, implies. Don't use an equal sign here. That would be a bad thing. Okay? You don't want an equal sign. Okay. Oops, kind of scroll a little bit too far there. Okay, cool. Notice that I'm saying it's not equal to this, and yet look what I just found. I guess in a way I could even, just to make a point here, I can move that minus sign to the other side by multiplying by negative 1 on both sides. Regardless, what I'm getting at is we have this problem that we just said not this is equal, and yet here we just said it's equal. That's that proof by contradiction. So at this point, I do a little exclamation mark thing and say, contradiction. This is not good, problem. Therefore, my negative v is unique to v, I guess, in v. Good enough there. And there you go. Done. We contradicted it. We're good to go. Moving on. Next section. 4.3 is about subspaces. Subspaces of vector spaces. Okay, now be careful with the language here. There's a whole lot I'm gonna have to do here, okay? So this is called the test for subspace, okay? This is kind of like the definition. If W is a non-empty subset, I'm gonna underline the set. Be careful, okay? This language kind of gets weird. A non-empty subset of vector space V, okay, comma, then W is a subspace of V if and only if the two closure properties hold. Two closures hold or something like that, okay? I'll just put hold right here just because I think that'll work. Okay. So let me, or closure conditions or something like that. Let me go ahead and list them out just one more time. I already know them, but this is more proper here. I guess I got if U, V are both elements of W, then my U plus V is also an element of W. So this is the closure under vector addition. Okay, let me pause the video for just a second here. All right. And number 2 is if I have U element of W and C is an element of the reals, then C times U vector is still an element of W. Again, this is called the closure under scalar multiplication. Okay. I was also taught that there was the need for like the additive identity and all that kind of stuff as well. This is good enough. This is what the book says. If you can do this, then you also must have all these other things as well. It's kind of just implied, I guess. Good enough for this class. So just let's go over it just one more time because this is a very important topic. We're going to be using this a whole lot as we keep going. So I'm saying that W is a subset of vectors. So we got a group of vectors that come from, I don't know, Rn, basically. So I got a big group of vectors, 3, 5, 10 of them, something like that. And it would be a subspace, if and only if, so both ways, if we have the closure properties hold. So if you have the closure property hold, then you know it's a subspace. If it's a subspace, you know the closure properties hold. And so I'm just grabbing a couple of these. I'm going to make sure that they work within themselves. Notice that they're not an element of V, they're still an element of W, okay? So they stay within themselves. Let me give you an example. And the book had something similar to this. Let's just say I have a vector V in R3, okay? And I'm going to define it as A0B. A0B, okay? Given that A, B are elements of the reals, okay? So I basically got two numbers here and there, but I got a 0 in the middle. Uh-oh. Can you actually get all of the vectors self-containing this way? I would say yes, actually. They would still be this way if I added one of these guys to another one. Just as like an example of an example, I guess you can say. Let's say I had 1, 0, 2, and then I had 3, 0, 4. Well, I'm going to add these. I got a 4, 0, 6. See how it's still got a 0 in the middle? That's what I'm kind of getting at. I'm saying, look, this style should be able to be okay. Here's another one. What if I did 3 times 1, 0, 2? Well, then I would get 3, 0, 6. Notice that again. I got that 0 in the middle. So this style should be okay. It should work within itself. And so what I'm going to do is just quickly mini-prove it to you. I'm going to say I have a W, which is now a C0D. And define those as real numbers. Okay, and so then I've got V plus W would then be A0B plus C0D, which would yield A plus C, 0, B plus D, which is still an element of, I don't know. Let's just not use R3 here because, yeah, it is R3, but I'm not trying to prove the whole entirety of R3. Let's just use a W. I mean, it comes from R3. I guess that would be like V, and this is its subset, I guess you can say. Notice that it's still got that 0 in the middle. That's the main point what I'm trying to make here. We still got the 0 in the middle. So I just did the additive closure under vector addition. So then let's just now say E is an element of the reals. And then I do EV would make EA0B when I distribute EA, 0, EB, and again, that's still an element of W. So again, does it have that 0 in the middle? Yes, we're good to go. So there you go. Box it in. We're done. That was not like a super great proof. I'm just kind of showing / proofing. It's kind of a proof. I just didn't do all the fancy doodaddy things along the way. 4, 3, 5, 3. Okay. So here is the proof. Let A be a fixed 2x3 matrix. Okay. I'm going to prove that W is equal to, and here's my set, X element of R3, as long as A X is equal to 1 comma 2. Okay, and I'm going to prove that it is not a subspace. If I can just write subspace. Okay. Of R3, right? Okay. Prove that it's not a subspace of R3. So, first off, I'm saying that this is a fixed matrix. I do not know what those numbers are, but it's a 2 by 3, so I got 2 by 3, I don't know, 1, 2, 3, 4, 5, 6. I'm just making something up. I'm saying, look, hey, this is what it looks like, but that is not the only one that it could be. Again, they didn't specify, so I better not specify either. I know that they're fixed numbers. I don't know what those numbers are, so I can't just assume like, oh, they're all zeros or they're all ones and twos. Obviously, they're ones and twos. I can't say that. And I'm trying to say that this is not in the subspace. This is actually a very simple proof, and I'm going to show you just in one single second, but I want to explain it here. The point that I'm going to make is that what I was taught whenever I was in my graduate classes even, it was called the squealing pig. I know that's kind of weird, but it takes only one pig to upset the bunch. If you got one pig that's freaking out and running around, all the other pigs are going to run around and freak out as well. What I'm saying is I can find one instance of this thing not working, the whole thing's not going to work. That's my point. I'm going to find one thing that doesn't work, and then they all won't work. Okay, that's basically the idea here. And so I'm going to let my x equal 0, 0, 0. Now, I could have chose some other numbers, but I specifically chose 0, 0, 0 on purpose. And I'll show you why. Thus, my ax would be, if I multiply a 0 right here into whatever matrix, I don't know, think again like the 1, 2, 3, 4, 5, 6, and I multiply this with 0, 0, 0, what do you think you're going to get out of this thing? What's your answer for this? It's probably going to be 0, 0. In fact, I know it's 0, 0, of course. It has to be. Because you're multiplying everything by 0, well, you're going to get 0. So my result will be 0, 0. That is not equal to 1, comma 2. Okay? So, ta-da! Doesn't work. Therefore, W is not a subset. Subspace. I don't know why I wrote subset there. Subspace. And this kind of is interesting as well. I use the additive identity on purpose. I'm sure there's other numbers out there, but I chose the additive identity because it's kind of implied by our use right here, this closure stuff. I know I didn't, again, I mentioned it. I'm just saying this subspace better have that 0, 0, 0 to make this thing work. And it doesn't. Therefore, the thing doesn't work. Okay, so that's my squealing pig proof, I guess you can call it. All right. For 4, we got a spanning set and linear independence. Okay. Spanning set and linear independence. So, let's start with a linear combination. And I feel like we talked about this back in chapter 2, but maybe I didn't. I don't know. But I got my vector v is C1 U1. I don't know why I didn't write a 1 there in my notes. C2 U2. Da 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 da. All the way to CNVN. I don't use n actually. I've been using k a lot because k is just kind of like k is just a number. K for constant. So my linear combination is that I have a vector is equal to a whole lot of other vectors added together with a scalar in front of each one, where Ci is an element of the reals, and Ui is an element of Rn or V or something. I think V is probably better at this point. It's fine. For all I less than or equal to k. Okay, so that's like a way basic-y, but not right proof. I don't know. I could probably say a little bit more there, but it's just saying, hey, for all these numbers here, we got a scalar, we got a vector. I'm just trying to make it, work, I guess. So that's a linear combination, is this kind of setup. And I guess I could give you an example of this. I don't know, let's just say that I had 3 times 1, 2, 3, plus 4 times 4, 5, 6, and 7 times 8, 9, 10. I have no clue what's going on here. You're going to get some big number, but you'll still get a vector out of the thing, So you multiply them, you add them, you get a vector, everything's good. So that's a linear combination right there. Okay, but I'm erasing all that because I don't know what that answer would be. That's a little bit too much math right now. Let's keep going to another definition. So I got if S is equal to V1, comma V2, dot, 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 all the way to VK. So if you have this set here is a subset of vector space V, then S is the spanning set. I'm going to underline that, spanning set of V if every vector in V is a linear combination of S. Is a linear combination of S. You would say that S spans V. So that's kind of like the quick version of this. So what does that mean? Well, I'm picking a set of vectors that can create any vector out there. Now, there's another name for something like this in just a little bit, but we're going to say spans is fine. And so here's my own example, and this is a very basic example. I kind of like this one personally. I got 1, 0, 0. I've got 0, 1, 0. And I've got 0, 0, 1. This is a spanning set for R3. I can create any vector in R3 using these guys in a linear combination format with a scalar in front of each one of them. So, like, let's just say I wanted to find 1, 2, 3. If I wanted to find that vector, that's part of R3, right? Well, how would I do it? Well, I'd say 1 times my V1, 2 times my V2, and 3 times my V3. I know that's kind of silly, but like, let's do another one. -4, 7, 9. So I put a -4, a 7, and a 9. It's almost silly. You're thinking, well, that's kind of easy. Well, yeah. But there's other vector sets that span this stuff too. This is just one of them. There are others. This is the most basic one. But like, could 1, 2, 3, -8, 9, 10, 0, 0, 1 still work? Maybe. It just kind of depends. We're going to see how we can find that out. Actually, that's exactly what I'm talking about here. So how do you know what vectors will do this? So how do you know if it works? If it spans? I like that. There's 2 ways. First off, you can say the determinant equals 0 would be not working. Okay. So if you find the determinant of these vectors, like right here, these 3 guys, put them together, and you got a 0 out of it, then it wouldn't work. Well, now these actually do not yield a 0. If you recall, you can actually multiply the diagonals and you get a 1, which is not equal to 0. So this is good. Okay, so that would work. So that's one way to do it, determinants. The other way is that you could RREF it, and if it equals IN technically, then it does work. Okay. Another way to do this is, I don't know, let's just say I had 1, 2, 3, 4, 5, 6, 7, 8, 9, something kind of like that. Ooh, so ugly. And I said RREF on this guy. And if I yielded out of this, computer obviously let it do it. If you got this, then you'd be good to go. And yes, these three vectors would be a spanning set. I don't think that would work personally. I haven't checked it. It might work. But you're looking for the identity matrix out of that. And if you did get that identity matrix, you're good to go. So two different ways of testing to see if it'll work or not. So it kind of depends on which one's more flavorful to you or maybe better for your proof. There is also this linear independence stuff. Independence. So linear independence is when you have C1V1 plus C2V2 plus ... all the way out to your K. Trying to get that all there. CKVK is equal to 0 vector only if it's C1 equals 0, C2 equals 0, all the way to CK equals 0. Okay. I was going to say this is trivial solution. I don't want to go there. I don't think that's right. So regardless, what I'm kind of getting at with all this is that I'm saying the only way to get a 0 answer from a linear combination, I mean, I guess you could even say this is like your U vectors equal those stuff. The only way to get it is if all your scalars are equal to 0, okay? That's linear independence. This kind of goes along with the whole determinant not equal to 0, REF, it goes to I and all that kind of stuff. If you remember, this is college algebra, if you RREF and you didn't get I, then they were dependent. It's a dependent solution. So it kind of just goes way, way, way back in the day to our college algebra times. I don't expect you to remember that. That's what I'm telling you. So 4468. So I got prove that if S1 is a non-empty subset of the finite, I don't know if that's going to be important or not, the finite set S2, comma, and that's a comma right there. I know that's kind of weird with all these subscripts. And S1 is linearly dependent, then so is S2. Okay, now what is going on here? I'm proving that if S1 is a subset of S2, okay, so like here, just a picture right quick. I got S2 is the big one, okay? And then inside of that, I got S1. It's a smaller one. So it's a subset inside of S2 there. And S1 is linear dependent. I'm saying, well, that makes then this whole thing here linear dependent also. Okay? That's the proof. We're trying to find that thing out. Of course, none of this is just pictures of what's going on. Let's actually do the math. So I gotta say, I'm a little disappointed. Is this the one? Yeah, I'm kind of disappointed in this proof that I did. It's not exactly the best. And there's a couple others that I feel this way as well. I didn't go and look any of this stuff up. I just did it. So I'm gonna do it. It seems fine to me, and that's good enough. There's obviously many answers and ways that how to prove these things. Okay, you'll see a couple more proofs coming up that are maybe a little disappointing as well. But that's okay. I mean, I'm not looking for perfection. I'm just doing it. You're just doing it. That's just the point, okay? So do whatever you think is right. I did this one. Here we go. So suppose that I have S1 is a subset. Now, this is a kind of an interesting symbol. We don't use it. It's a little U and then a line beneath it. So it's not like it's not less than or equal to. It's actually like a U-shape thing, like a C, kind of like a C with a line underneath it. It means subset. And I put the line underneath because it's basically also having the 0 vector, I'm guessing. I mean, another way to do this is just having a C And so, but I'm going to put the equal sign. It kind of indicates that there's like a additive identity and all that additive inverse stuff. Moving on. Of S2. I'm just showing you symbols, I guess. So I got this subset here, and S1 is linearly dependent. Okay, now keep in mind this definition up here as we go through, okay? So linear dependent is not independent. It's this thing, but it's not that way, okay? It's the opposite of that. So here we go. I would say then, thus, V, I'm going to make some vectors up, x1, x2, ... all the way to xk. I'm just using k because it's cool. K is cool. Element of your S1 and C1, C2, CK, element of the reals. Just defining all my numbers, you know. I don't know, on my paper I wrote something else there. Whatever. It's the reals. Okay, cool. So I got all these variables I just set up, and so let me go ahead and start setting them up. V is equal to C1x1, C2x2, ... CKxk. Cool. And I'm saying that this is equal... No, it's equal to 0 vector when, or implies that there exists some kind of C1 not equal to 0. Now, this is a symbol I haven't used yet. I might have used it on one of the, you know, the proof answers or something like that. But this right here means there exists. It's an E backwards. There exists. Just like an upside down A is for all. This is there exists. There is a single one. Some CI, sorry, I meant CI, is not equal to 0. That's that linear dependent stuff, okay? I'm saying go back to the definition saying that all of them are equal to 0 for independent. Well, then now, because they're dependent, one of them's not equal to 0, and yet I'm still yielding a 0 here, okay? Now, what could happen, just on the side here for a second, I could have that x that's associated with it. I don't know, let's just say that c that's not a 0, let's just say it's 2. So there's my ci. But let's just say my xi was a 0, 0, 0. I would still get the 0, 0, 0 out of it, and therefore everything still works out fine. 0 here, 0 there. This guy here is 2 times 0 is still going to be a 0. So you add zeros up and you're good to go. But that's a trivial solution. This is what that trivial solution stuff is. I wouldn't just say, well, of course there's got to be a 0 there. It never said that, did it? It never said that. So don't go into that territory is what I'm trying to say. We got this weird thing that somehow I'm saying 0 plus 2 is still equal to 0. Okay, that's what's going on. 0 plus something else somehow still equals 2. Right? So how does that work logically? This is my next step in the proof here, okay? How do I still make it equal to 0, yet I know that I have one of these is not 0? Well, how about this? What if I had a negative 2? Wouldn't negative 2 and 2 both make a 0 now? And therefore 0 plus 0 plus 0 equals 0? You see what I mean? So in a way, I'm now saying not just one of these is not equal to 0, but probably there's another one also not equal to 0, okay? So let me keep going. So assuming that my xi, the one associated with this guy, is not equal to the 0 vector. Again, I just talked about this as a trivial solution. Trivial solution. We're not talking about that guy today. There must also be, I like also be a Cj not equal to 0. Okay? And thus, I got a xi is a scalar multiple of xj. Okay, now this is kind of interesting. This is a big leap right here. Let's pause and talk about it for a second. I'm saying that I have this this one here that's going to work, and somehow I've got to make this 0 thing still work here. Let me go back to my example. I got a 0 plus a 0 plus a 2 somehow equals 0. And I say, well, that doesn't work. I could put a negative 2 in there, and then it works. I'm not going to say that these are necessarily like inverses of one another, though it's probably going to be that way. Inverse in a kind of a weird way. They're kind of like inverses of one another. But what if I had, just as an example here, I'm trying to make that 0 over there. Remember how we always have vectors associated with all this stuff, right? So let me rewrite it. This is my logical thoughts here. I had a 1, 2, 3. I had a 4, 5, 6. And then way over here, I had like, I don't know, 7, 8, 9. And it still equals 0, and I had a 2 right there. Remember that each one of these still has a vector attached to it, right? Well, 0 times anything is 0, and that's why I was just able to put zeros here. And I said 2 just as a simplification, but it's not just 2, is it? It's actually a vector, a whole vector. So if I'm going to insert that negative 2 business and still yield the 0, that's got to be the same vector twice. It's got to be the same vector twice with a negative, and then it's going to make a 0. You're thinking, well, is there some way to make it not, exactly the same? Well, yeah. What if I replace this here with a negative 1, 14, 16, 18? Would I still make a 0? Yes. But look at this vector. It's still a scalar multiple of the other one. I just took that 2 and I moved it inside. That's all I did. These have got to be related somehow. They're related somehow. Therefore, they can cancel and still yield the 0 in the end. They've got to be related somehow. That's that linear dependent stuff. There's an extra vector that doesn't belong in the whole big grand scheme of things. But that's again, a little bit further. So that's my logic for that. If on your proof, when you're writing it for me and you do this kind of stuff, it's cool to be able to tell me blah, blah, blah on the side. I mean, kind of like what I was just telling you and stuff. It's good to inform me of what you're doing. I don't mind. I'm not going to count off one way or another. I would say it's just good. That way, if I'm confused, like for me, honestly, this is a pretty big leap, and I would have probably wanted just some kind of side note, I guess. Like, oh, and how do you assume this all of a sudden? I'd have to sit there and think about it a while. And so you can do something on the side and kind of talk about it and whatever, English or math or an example or something like that. But just remember, that's not part of your proof. That's just you helping me out so that I can remember when I'm grading, okay? I'm just grading here. It doesn't mean anything about your proof. Your proof is fine. If I count it wrong because I didn't understand, you can contest it and I'll, regrade it, and that's fine with me. I'm totally okay with that. So this is good. Everything is good so far, okay? So I have got these two different vectors that are scalar multiples of each other, okay? Interesting. Because S1 is a subset of S2, S2 also has my xi and my xj. Again, like that Venn diagram stuff, if you have xi and xj here, well, then they're basically also part of this box, aren't they? The S2 box. Thus, S2 is also linearly dependent. Fill it in or not, whatever. Done. In a way here, this might be a small little leap from here to there. I'm kind of saying that the same properties exist here. Like if you're doing all this math and you're having these issues with linear dependent, well then you got the same troubled folk in S2. They're going to do the same thing to that guy as well. The end. Okay. Next section. 4.5. Basis and dimension. Okay. There really wasn't as much to talk about here. I think it was just a continuation of 4.4. But a set of vectors, S is equal to, and then I got V1, V2, ... Vn. I think it's important to add the n in this particular case. No, I can't remember. K, n, whatever. Is, or I'm sorry, in. Yeah, is. No, I'm sorry. Let me reread it. A set of vectors S in vector space V is a basis. There's my keyword basis for vector space V if or when part 1 S spans V and 2 S is linearly independent. To me, these kind of go hand in hand, but I'm not going to go that far. I know there might be a possibility where a linearly dependent system might be able to still span V, or maybe there was an additional vector because it wasn't the least common multiple of it or something weird. Trying to relate it back to real numbers. It needs a span and be linearly independent, and this would be called a basis. So if you have a minimum amount of vectors that still spans it, you're basically going to have that linear independence already. Therefore, it's a basis. Okay, so here's my classic example for a basis of R3. Let's say 1, 0, 0, 0, 1, 0, and 0, 0, 1. All the properties that we used above with the linear combinations, linear independent, spanning, and all that kind of stuff, they all apply. I'm just saying, as long as you got both of these, then you got a basis, which is almost always the same thing, but, you know, that's why there's a new section for it, I suppose. Cool. So that's my basic set right there. Can I make any vector in R3 from those three vectors? Yes. Are they linearly independent from one another? Yes. Well, then you're good. Check mark. Check mark. We're good to go. Now I just ask myself the questions. Okay. How would you prove that? You would go back to the last section to prove each one of those individually. Okay. So here's another one. So prove that if S is equal to V1, V2, all the way to Vn. I think I'm using n necessarily here because this is like, again, R3, so then I've only got 1, 2, 3 different vectors to get that done. That's that whole linear independent stuff, okay? I need a minimum set of vectors that all of them actually create vectors in that space, okay? So that's kind of what I'm getting at. That's why I'm probably using an n here in my notes, not a k, is a basis. So we got all these vectors as a basis for vector space V. Now, I'm saying vector space V. I probably ought to write it. I'm just kind of lazy right now. Vector space V. And C is a non-zero scalar. This is all part of the proof here. Then the set S1 equal to, this is my problem here, C V1, C V2, dot, 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 C Vn is also a basis for V. Okay. What they're saying here, this is my question. They're saying prove that we have a nice little basis here, and then I slap a C on the front of them. So I don't know, a 2, and a 2. It's got to be the same number. Got to be the same number. It should still be a basis. So is that true? I would say yes, definitely. It's very simple and easy process here. My proof is it's very compact. So, sometimes that's okay. Here we go. Here's my very compacted proof. D1 CV1 plus D2 CV2 plus dot 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 is equal to C times D1 V1. I'll explain myself in a second. D2 V2 plus dot dot dot. And then I said this is still an element of V. And then for all DI. This is very, very quick little mini proof, okay? I just didn't have enough room to put that over there. what I'm going for is this linear combination stuff. Again, for a basis, it needs to be linearly independent, means I had to do the linear combination stuff, and spanning is, well, still a linear combination stuff. So I'm doing this linear combination using D as my scalar for each one of them. But remember that C is a constant, and it's always the same for each single number. It's always a 2, let's say. Well, I just factor it out to the front, and don't I have a vector here that's in V, and I just multiply it? Yeah, so we're good to go. Everything's fine here. So basically it proved that the linear combination still works, and we're good to go. That might be enough for this one to be done, but I'm going to go on just a tiny bit more. I'm going to say that, and the matrix, and I got a CV1. This is kind of weird about matrices. I'll explain myself here in just a second. CV2. Okay, now let's just pause here. I'm actually making a matrix here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm actually doing this in front of you. You're just not seeing it because what I'm doing is V1, V2, V3. These are columns. That's each column. And so this guy right here is V1. This guy right here is V2. And this is V3. I'm just writing a matrix. This is a full big old matrix, you know what I mean? But I'm only writing their columns in each case. So that's a column, that's a column, that's a column. And you can notice this difference in the book because they use bold, and here with me, I'm using a little arrow vector thingy, okay? So I have this big old matrix here, and I'm going to, of course, factor the C out to the front because that's part of my basic matrix operations. No plus signs, no commas. This is a matrix. No commas, no plus signs, just write them out. And I'm going to say that so these are equal. I'm going to say that the RREF of this C, V1, V2, blah, 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 would equal C times I, okay, because all these because again, it's linearly independent kind of stuff here, right? Yeah, because we already said it was a basis. So it's a basis, therefore it's linear independent, all that kind of stuff. I should get an I, there's a C in the front, but this here, it's kind of weird because technically I have the C in the front, I get a CI. What happens is technically I don't even have the C in the front, okay? Like, in a way, just as a quick little example on the side, what if I had this guy here, and I did RREF with that one in the calculator? What do you think I would get? Well, they would get rid of all my numbers, right? It would just be I. So this RREF should still equal I, even with the C there. So I'm removing the C. I know it's kind of dorky, but I'm saying, like, you can factor the C out, or you can leave it in, regardless. I'm going towards an I. I'm going to get an I in the end, and therefore we're good. We're linearly independent again. This is a basis. Everything's great. Linearly independent, and I can write it as a span. It spans it. I don't know. That's good enough. Again, some of my proofs today might seem a little like, what? Like, that's it? And yeah, I mean, that's it sometimes. 4.6, rank of a matrix. Rank. So there's this row space and column space, which are very similar in their definition. I'm going to do the row space. So I'm going to say the row space of a matrix A is a subspace. Again, look for these words, subspace, not a subset here. Subspace of Rn. Subspace means, again, we got the closure under addition and scalar multiplication and all that kind of stuff. Of Rn is spanned, and we just saw that in the past two sections, by the row vectors of A. That's kind of weird here. Spanned means linearly independent, and they can create all and every vector in that place there by the row vectors. Okay, so it's kind of weird. Row vectors are basically just 1, 2, 3 going this way instead of the 1, 2, 3 going that way. This would be a column vector. That's a row vector. Okay, well, there you go. The column space is identical to this. They just replace the word row with column, and you're got the same thing. Doesn't change anything at all. So I initially always think, well, column space is a lot more important then because that's what we normally use and all this kind of stuff. Well, they like to focus on the row space in particular in this section. I'm going to keep doing that as well. Regardless, the row space and the column space have the same dimension. Have the same dimensions. Have the same dimensions. Anyways, and that's called rank. That dimension, it's called rank. There's a title for you there. It's the dimension of my row space. So here's an example. I actually took this one from the book because, I mean, it was kind of easy to see and all that. I just wanted to give you an example of what's going on here for the video without me trying to guess at some numbers that might work, just as nicely. So I take this matrix, I do some RREF with it, and I got 1, -2, -5, 0, 1, 3, 0, 0, 0. So that was my RREF. I know that doesn't look like RREF. That's why I'm saying all this stuff. RREF. And it's kind of interesting because, look, if you can see here, I've got 2 rows that are still around. You see this guy? He's not really a set of numbers anymore. He's just gone. So I got 2 rows. Therefore, my rank is equal to 2. These would be my row space. That would be my row space. The column space is actually, you're just going to take those and you're going to translate them, transform them, transpose them. There it is, transpose. Like with the little T at the top, transpose. Sorry, it's been a while. Trying to remember back in chapter 2 there. So cool, we got a rank of 2. Okay, so if you had the I for the identity matrix and you RREF, you got that, well then it would be 1, 2, and 3. Your rank would be 3, and your size would be a 3. The thing is that this is a 3x3 true, but we're going to be focusing more on this guy right here, here in just a few seconds, and I'll show you what I mean by that. Because obviously you don't have to always have a 3x3, you can have any kind of size and still do all this math here. Continue on. The set of all solutions of my AX equals 0 is a subspace. Again, subspace, kind of interesting there how they're saying that, of Rn, that's called the null space. I think that this term will come up more often as we keep going through the class. I can't really remember. Anyways, they like to say capital N, capital A, null space of A, that kind of thing. So let me go ahead and give you the most formal definition that they even give you here. My null space of A is equal to X element of my Rn such that AX is equal to 0. So find all of the solutions that yield 0, and you're thinking, well, it's 0 vector, and you're right. That's why you can have a subspace, because you have the additive identity, closure under addition, and all that kind of stuff here. I'm basically making a point that, yes, you do have 0. It's a trivial solution, right? That's a trivial solution. Could there be more than just that? Could there be another vector that also could yield a 0? And that's kind of going to be the question here in a minute. The dimension of the null space is called the nullity. So null space nullity. There you go. So the dimension of this, the dimension of that. So let me make a point here. We got A is an M by N matrix. The sizes here are very important this time. Remember, we're going to focus on the second guy here, okay? If we have that, my N is equal to the rank of A plus the nullity of A, okay? The dimension of the row space plus the dimension of the null space should equal this guy. Going way back to my example right here, I'm just going to go ahead and rewrite it if that's okay. It's a negative technically. 0, 1, 3, 0, 0, 0. Notice that we have right here 2 is my rank, my rows, and then I had this one dude which was zeros, right? Null space. So 1 would be my nullity. And so then I had 1 plus, or 2 plus 1 is 3, which is my number of columns. This guy right here, 3. There's 1, 2, 3 of them, and therefore it all works out. You might be wondering how I can get a number of columns from just some rows, right? These are rows and all that stuff. Well, technically here what I also use, I'm going to use a different color to show you. Notice that these guys descended. I went from one to the next here. But here all of a sudden I did not descend. So I'm saying I had the 2 that worked and the 1 that didn't work. Okay? That's another way to detect that stuff, using columns, I guess you can say. So in like a more like bigger one here, and I'm going to use just all kind of numbers if you don't mind. 0, 1, 4, we already had a 4, 6, 7, 8, 0, 0, 0, 1, 9, 0, 0, 0, 0, 0. There we go. In fact, I don't even need those zeros on the bottom. Let's just get rid of that. Okay, this is what I got. Notice that we had a descend right there. Nothing right there, but a descending right there. These guys are multiples of this stuff in a way. It's like you could see that basically there's 3 that worked. We had 2 that didn't work. So I'm going to say nullity. And then you add them together and you get 5. So, and that would be 1, 2, 3, 4, 5. There you go. And that's just the other way you can do it. I'm going to keep going here. You can also see, if you don't mind, like, well, you're just watching a video here. You can see that we had 3 rows that were non-zero, correct? 3 rows that are non-zero. Well, we know that we have 5 total, so then what would be the nullity? Well, it's 5 minus 3 is 2. Okay, so that's another way to do that. There's a lot of ways to find all these numbers. I don't know why I put a line there. We're going to actually do some math now. 4, 6, 79B. Only B here, okay? Because there was like 2 parts to it. So A is an M by N matrix. Prove that the homogeneous, let me try to spell it correctly. And I'll describe that here in a system, in a second. The homogeneous system of linear equations, AX equals 0, has only the trivial solution. If and only if, there's a key little thing we're going to have to look out for. The columns of A are linearly independent. Linear independent. Okay, let's talk about this. There's a lot of stuff going on with just this little proof. So, homogeneous basically is you do something to it and you get a 0. Okay, or the whole system equals 0. Okay, homogeneous basically ends up saying blah 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 equals 0. That's kind of what they're wanting to say there. This term comes up in other classes. I would also say another way you can say this is a non-constant. There's no scalar constant at the end or something like that. But equals 0 is probably going to be good enough for there. Well, this is not going to be super important because, well, look, it equals 0. That's the point here, okay? It doesn't equal B. It doesn't equal another vector. It equals 0, homogeneous. This if and only if is going to really bother me unless I actually do it correctly. I have to do 2 parts to this proof. I have to go one way and then the other. Again, I want to show you two different colors here. So we have this here has the trivial solution only, if and only if columns are linearly independent. So what I have to do is say we have the trivial solution. So I'm going to say if the trivial solution, then linear independent. So that's part one. And then part two is if linear independent, then trivial solution. Okay? I have to do both. I have to do both. Otherwise, you didn't do the whole proof, okay? All right. Let me see which one I started with. I started with the... Oh, okay. Well, I did mine a little weird. And again, some of my proofs today are not going to be, like, great. I look back at this proof and I'm thinking, you know what? I could have probably done that way easier, a different way. But I'm going to do it because I wrote it down. I would just want to show you that even I kind of do weird proofs sometimes. That's okay. Everyone does different proofs. So I'm going to do a proof by contradiction. You do not have to do this for this one. Honestly, I looked back and I was like, I could have just done this the basic way. Proof by contradiction, both ways contradicting. So number one, I'm going to say that my A, I'm going to simplify it a tiny bit. AX is equal to 0 has a non-trivial solution. Okay. Yet, A is linearly independent. Okay. So I'm going with this number one here, basically. So if it's independent, then by the definition, and this is actually pretty important here, by the definition of linear independence, which is way back a couple of sections ago, we actually wrote it down here on the video at some point. By the definition of linear independence, my AX equals 0 must only have the trivial solution. So, contradiction. Notice I said it has a non-trivial solution, but I must have a trivial solution. Contradiction. And so therefore, if A is linearly independent, I guess I'm doing number two, then it only has trivial solution. So I guess I did number two here instead of number one. It's kind of weird because it's proof by contradiction kind of go backwards in a way. So it's kind of weird. Again, you do not have to do it this way. I'm just doing it my way because I decided to do it this way. I don't know. It's just what I decided. So I'm going to go the other way. I'm going to assume, again, it's still proof by contradiction, that only the trivial solution exists, yet A is linearly dependent. So I'm saying yes, we have the trivial solution only, yet it's linearly dependent. There's no other solutions that work for this AX equals 0 stuff. If linearly dependent, there exists some x vector not equal to 0 that satisfies my AX equal to 0. Okay? And I guess you can say even way like my nullity is more than 0 or something like that. There exists some other x that's not equal to 0 because linearly dependent that should still make this happen. Whoa, hold on. Contradiction. Because if you remember, it's the only trivial solution that exists. I'm saying there's a non-trivial solution that exists. Contradiction. Therefore, AX equals 0 only has the trivial solution. then my A is linearly independent. Okay, whew, did it. The main part here, the proof by contradiction is kind of silly, and if you can notice, all I did here was say, go look up the definition of linear independence. I could have done this much better, but I just decided to show you. It's a small little goofy proof, and it works. And there you go. You do not need to do proof by contradiction. You do need to do two different ways for the if and only if. That is a very important aspect of that proof. 2 sections left. We're almost there. So 4, 7, we've got coordinates and change of basis. I actually really like this section, and I wish I could have spent more time on it, but we just don't got the time here. I got some x vector in B prime is equal to P inverse times that x vector in B, base B. So it's a base B prime, base B. How I like to describe it is we have here my B, and then I have here my B prime, and going from B to B prime, I'm going to multiply it by P inverse. Okay, now what does this whole thing mean here, coordinates and all this stuff? Let's just say over here I had my vector as 1, 2. I had some kind of point on this plane here at 1, 2. But when I did this move over here, I transitioned it, I changed this basis. My new one is 3, 4. Okay? Now, you're thinking, well, hold on. Couldn't I just multiply both of them by 2? No. Did a times 2 work? No, that didn't work. Well, I just add 2 to both of them. Yeah, but, like, I'm multiplying here. You can't just add something to it. So that didn't work either. You can't just add something to it. What am I multiplying by in order to get this, right? Well, it's a matrix. It's a whole matrix of some kind, and I have no clue what that is in this particular case. But I'm making it into a different place than it originally was. It was there, now it's over here on a new basis. And that's still kind of a primitive understanding of what's going on here. It's a very neat topic, and if you read through the book, it kind of helps a little bit more. But this is useful in all kinds of applications, especially with computers and graphics in particular. But let's move on before I go ahead of myself here. We're just going to do math here. The way to get P inverse is that you take your B basis prime and you augment it with your B basis, and then you're going to RREF, and you should get your I out of this augmented with the P inverse. Now, augment, what I mean is like a vertical line separating the two, and that's technically a very good way to do this. I think I would prefer it with the line. The book doesn't do that, but I like the line, the augment line, separating these two matrices so that we can actually get something useful, and it's not just a whole ton of numbers, okay? You RREF this huge thing, and it yields whatever you got. So let's just do an example. And so I have my B basis. This is a basis here for R3, I'm supposing. We got 3 vectors that are going to make any other vector possible in R3 as long as I scalar multiply them a certain way here and there. Well, I have another basis here. Again, a whole separate new one here. Nothing in relation to the other one, okay? So I got a whole different basis, and that works. I'm wanting to take a point from here and go to there somehow. So in order to do that, I have to multiply by a special matrix, that P inverse. Let's just say that I had 1, 2, 3 in basis B, and I want to know what is that in B prime. If I had over here in this coordinate system 1, 2, 3, what would it be? Would it be down here now? Would it be over here now? I don't know. I have no clue what it would look like, but we're going to find out. That's the point. So I'm going to take my B prime. Be very careful about the order that you're doing this, okay? Augmented. I actually put an augment in my notes. That's good. 1, negative 1, 2. I'm going to augment it with my B. Notice, B prime B. Then I'm going to REF it. Now, I already did this in the calculator, okay? Or whatever, Desmos, whatever you want to use. And I got this guy. Again, the calculator, Desmos, all that stuff will not have an augment. The book does not use an augment, as far as I remember. I like to use the augment because it reminds me these are two separate matrices. I'm just mushing them together. And I REF and I get this guy here. Well, that's my I, and this is my P inverse. This is what I'm going to multiply with this guy in order to get that. So what I'm going to say now, in order to get that B prime number, I'm going to take my P inverse, and I'm going to that is just not really great there. I'm going to multiply this by my 1, 2, 3. And I should get my answer. Okay, so I did that. In the calculator, obviously. And I got 29, negative 15, negative 25. A whole different set of numbers. Who would have guessed that 1, 2, 3 goes to 29, 15, 25? Well, nobody, but that's the point. It's a whole different, set of numbers here. But it is technically, I guess, that same point, just in a different basis. Okay, cool. Nifty. Again, I'm not going to go too far into it. Let's keep going. We're almost done. 4.8, applications. Now, there's, I think, about 2 applications they really talk about. There's the rotation of conics, which I'm not going to talk about. It's not on the quiz. I'm not going to talk about it here. So, but rotation of conics is really fun. If you haven't done it, well, it's probably good that you didn't do it. But I'm going to focus on the Wronskian, which is on the quiz. And basically, my really basic formula is y1, y2, y1 prime, y2 prime, y1 double prime, y2 double prime, You keep doing this, and this is one big determinant. Notice my vertical lines here. It's a determinant. And I'm wanting to see if, and they often just call it W for Wronskian. And I can tell if some differential equations are linearly independent or not, depending on the Wronskian answer. So they're linearly independent differential equation stuff if my W is not equal to 0. My determinant is not equal to 0. Well, that's the formula. Let's just go ahead and do an example here. I think the quiz basically just tosses it on you kind of like this. I'm going to go a little bit better, I think. But here we go. I got x, sine x, cosine x. And I'm going to just say, find the Wronskian and tell me what's going on. Okay. So I want to find my originals. I'm going to put my originals here in the top. And I'm going to keep going until I can make it a square matrix. Why do I need a square matrix? Well, because I'm finding a determinant. The determinant only works with square matrices, going way back into chapter 3 stuff. So I have to keep going derivatives as many equations that I have. So what's the derivative of x? It's 1. Derivative of sine is a cosine. And derivative of cosine is a negative sine. Keep going. What's the derivative of 1 is 0. What's the derivative of cosine? Negative sine. What's the derivative of negative sine is negative cosine. If it's been a while since you did derivatives there, just on the side note, you got your sine. I'll just write it the way I normally do it, sorry. Sine, cosine, negative sine, negative cosine. And just go down, 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 back up for my derivatives. My integrals go up. So integrals go upwards. And like this guy would go like this. It's just a chain thing. So derivatives, integrals. There you go. So I want to find the derivative. What I'm going to use is my cofactor. I think it's called cofactors. Or these guys right here. Way easier than trying something else. So I got x times my, again, you see how I'm doing my minor now. Cofactor expansion? Is that what it's called? See, it's just like the last section or two, and I can't remember. It's okay, all those fancy words. Do the math, it'll be fine. So that was a positive, now it's a negative. And again, remember that we're doing this, okay? So you're doing these guys up there. So sine x, cosine x. And then a negative sine x, negative cosine x. And then finally a 0. it's kind of funny, and again, you're doing this, so you got this big determinant thing right there. Well, anything times 0 is 0. You don't really have to deal with that anymore, okay? So just 0. Fine enough. That's what I have on my paper. I'm going to find the determinant of this guy. So cosine times a negative cosine is negative cosine squared. And then notice I got 1, 2, and then because this is the second, I guess, side of the determinant, 3 negative signs, yielding 1 in the end, sine squared x. I had messed that up on my own paper, and I was wondering, why am I not getting the right answer? Because I messed up that guy. 3 minus signs, 1, 2, and then the action I was doing was a third. I'm going to keep that minus sign in the front for just a second. We got a sine, it would be a negative sine cosine. And then here we got 2 negatives make a positive sine cosine. And that 0 goes away. Notice that we got a negative and a positive. These guys cancel. And then I can pull the negative sign out of these guys. So I got now, more properly, sine squared plus cosine squared. If you remember, this guy yields a 1. There we go. Now, notice that I'm saying, hey, is it linearly independent? Well, it's not equal to 0, is it? Is this equal to 0? No, it's not equal to 0. It's equal to x, or whatever. So I would say linearly independent. The only time that this would be not linearly independent or something that's kind of like not working right, something's not working here, is if x is actually equal to 0, then I would get a little worried because obviously we'd have 0 equals 0. But that's not the point. That's, again, notice x equals 0 is a single solution to this differential equation problem, and you would get a whole lot of messed up stuff, and it might even be a trivial solution or not, I don't know. Is this literally equal to 0 every single time? And I would say no, linearly independent, you're good to go. All right, that finishes Chapter 4. If you ever have questions, let me know. Thanks for hanging out. Have a great day.